All right, so we're starting at number 7 here, folks. Remember, I recommend that you, if you don't have number 7 complete, work in parallel with me and ask any questions along the way. If you do have number 7 complete, feel free to work on a different one. And there are some people who might even be able to help you on that one if they have 7 complete also. So with 7 here, what they're asking us to do is add together 2 vectors, and the vectors happen to be in 3 dimensions, and they tell us their components. There are a lot of different ways to write vectors. We only went over 3: compass, angle, and unit vectors. So this is another method, but what they're telling you here is the components of the vectors, the x, the y, and the z components. So what I'm going to do is translate that into unit vectors so that I understand it better. All right? That's going to be my first task here. I'm going to translate these 2 vectors and write them down as unit vectors to hopefully help me understand them better. So the first one tells me it's 2.8 in the x, 1.1 in the y, and 0.0 in the z. So this is number 7 here. And I'm going to actually do this in the how part. I'm going to write V1, and let's see, that was 2.8 in the x. So I'd write 2.8, and our x unit vector is I, and then 1.1 in the j, so plus 1.1 j, because that's in the z, in the y dimension. And then my last one was plus 0.0 k. Or I suppose if it made me happy, it'd be just easy to put negative 0.0, right? And go either way. And now my second vector, v2. Let's see what it gives me. Components of 3.7, -3, and -2. So 3.7i minus 3.0j. I could have also written plus -3, right? Or write it as just -3, either way, whatever makes it more sense to you. And then minus 2.0 k. And so those are the 2 vectors. First thing, now, drawing a 3-dimensional vector, while it's not impossible, and it just takes a little more kind of spatial ability than drawing a 2-dimensional one. And I realize that not everyone is able to see that. So here is what I would grade as 100% correct for the y for this one. And then I'll show you what it would actually look like, okay? So for grading purposes, if you had given me this, V1, V2, and then this we'll call, what do they want it to be? V. If you had drawn that, showing me V1 added to V2, and the resultant is V, full credit. All right? What it actually looks like, oh, this is the fun. I'm going to draw a little plane here. Kind of like you're looking at a sheet of paper. Trying to draw perspective here, yes? Can you guys see that, kind of? We're going to say y is in that direction. We'll say x is in that direction, and then z is straight up. So remember, x is the same as the I direction, y is the j direction, and z is the k direction. And so what this is telling me is that v1, the vector v1, is made up of 2.8 units in the x direction, 1.1 in the j direction, and none in the k direction. So for that one, Um, I would go this way, 2.8, this way, 1.1, and then none in the z direction. So that would be my v1 vector, drawn in a 3D sense. My v2 looks a little more complicated. It goes 3.7 in the x. Oh, and these should all have arrows on them, right? Sorry, me being delinquent. Negative 3.0 in the j, so that means down this way. And then negative 2 in the k, which means it goes down this way. So my vector there, hold on a sec. My vector there would look like something like that. Yeah. Well, that's what we're going to go into. We're going to go into how to add these together. So really what I should do is make these add tip to tail. Come on. There we go. And I missed one of them here. So what I should do, I still missed one of them. Never mind. I should add these tip to tail and move them around. The nice thing I like, one of the reasons I like unit vectors is to add these two to vectors. Remember, we had that whole discussion the other day about if I could add two numbers together, or I could break those two numbers into their parts and add the parts together. Yes? Is that in here or in my other class? But, so, if I want to add these two vectors together, I can also just add up their parts. And that tells me the new vector. So, v1 plus v2 is v. I just add down my column. 2.8 plus 3.7 is 6.5. This is the first I'm working on it. Minus 1.9j minus 2.0k. And those would be the components of the addition of those two vectors. So that's what I'm going to check. Let's see, 6.5. Let's see if I got it right. 6.5 and negative 3 and negative 2. Let me see if I got it. After all, it is Wednesday. And I think it is. Ooh. I got the negative 3 wrong. Oh, because I put in negative 3 and it's negative 1.9. Because I wrote in the wrong number. I haven't gotten to that part yet. No problem at all. Alright, so now that I typed in the correct numbers, I've got those correct. So now, does everyone see how I got those?
Yes.
Alright. Yeah, because that's what you're doing. And that's the nice thing about components, is they face in the same direction, and we know how to add things that are in the same line. We've learned that like many years ago in math. And if not, we're learning it now. It's when they're not in the same line that we have to be, use the trigger. That's why our main way to add things together is to break them into parts that are all in the same line, and then add those as far as we can. Okay? That's to show that you understand why you're actually doing it. The reason the why this works is because of all their components lining up. Yes, but remember, because I realize that different spatial abilities, this shows me the same thing as this. Now technically, what I would what you could draw on this to show the exact same thing is I'm going to have components like this. There are the components of V1. And then the components of V2 are like that. And the components of my last one would be like that. So, it's the green vertical plus the blue vertical adds up to the red vertical. The green horizontal plus the blue horizontal equals the red horizontal. So that's kind of what I've done here, is I've added up these are all my horizontals. These are all my x's. These are all my y's. These are all my z's. All right? And I've gotten an answer now in x, y, and z. I've gotten the three red components. But now they want to know what's the hypotenuse of this triangle. All right? They want to know what's the length of that black final vector. Well, to do that, I have a three-dimensional vector. It's like this little diagram, this little model I have up here. We're looking for the green here. All right? What type of triangle is this? The right triangle. So as long as we knew the two legs of it, we could use Pythagoras to find the hypotenuse. Right? Well, and then we have this triangle that's on the ground. That's also a right triangle. Yes? Okay? So this is what our actual vector looks like. And it's two right triangles joined at the hypotenuse and the leg of one. And if you need to see it closer, that's why I made this, so you can come up and look at it. Because it's really kind of a mind-bending, weird, trippy idea. All right? But what it all boils down to is these two triangles that are joined together in such a way that it comes up to what I call three-dimensional Pythagoras. Because we know, what's Pythagoras? A squared plus B squared equals C squared. If you do that with two triangles that are joined, you can do A squared plus B squared plus C squared equals D squared. And just, if you want to see the proof of it, it's in that little model that I built, and I can walk you through why the math works. The other thing is, this is on our equation sheet, and I call it three-dimensional Pythagoras. Because if I put in my x components, my y components, my z components, I get my overall magnitude of my vector. All right? So, in this case, I'm going to put in 6.5 squared plus. Now, does it matter if I put in negative 1.9 or if I put in 1.9? Let's think. Let's do it with numbers that I can do in my head. What's negative 2 squared? 4. What's 2 squared? 4. Does the negative sign matter when I'm squaring a number? No. I choose to not put it in because it's one more mistake I could make putting into my calculator. So I choose not to put them in. This is 2 squared equals v squared. And we're looking for v. And this is where I need my calculator. Squared plus 1.9 squared plus 2 squared equals 49.86. So v squared is 49.86. But what's the most common mistake at this point? To forget to square root it. And I don't want v squared, I want v, and I get v equals 7.06. Now I gotta see if that's right. And I got it. Okay, so we're looking at number 8 here. and they give us a plane traveling at 735 kilometers an hour in a direction of this west of north. So that means I start pointing north and I swing 40.5 degrees west. And they want me to find the components and then how far it's traveled after 3 hours. So I'm going to be lazy. I'm going to grab my vector diagram here, so I don't have to redraw it, and make it nice and big. Did that work? So this is number 8. Did that work? So I need to find the northerly and the westerly components of my vector here. So what I'm going to do is I'm going to draw in those two components. My northerly component would go that direction. My westerly component would go that direction. So I have this triangle. I have a right triangle now. I know that the length of my vector, the length of that hypotenuse, is 735 kilometers an hour. And they told me this angle in here, I kind of obscured it with my drawing, for me is 40.5 degrees. Everyone has different values for those, yes? All right. So now I want to find what are the legs, what are the two components. Let's name this component N, and we'll name this one W. All right? N and W. So I look at, oh, it's a right triangle. I have ratios, SOHCAHTOA. And so which one do you want to find first? North is that, and they asked me for northerly first. That's a good plan. So I'm looking for N. N is next to, or what we call adjacent to the angle. So I know adjacent is cosine, right? So cosine of theta is adjacent over hypotenuse. That's the ka part of SOHCAHTOA. So I'm going to put in my values. Cosine of 40.5 degrees equals adjacent, which I called N, over the hypotenuse, which is 735 kilometers an hour. Did everyone see okay? Now I need to solve for N, so I'm going to bring the 735 kilometers an hour over on the other side by multiplying it to both sides. So I end up with 735 kilometers per hour times cosine of 40.5 degrees equals N. Yes, ma'am. Yeah. It sounds like you could have also, I mean, you've got the freedom to draw your triangle different ways. You could have drawn your triangle west and then north. And then you just need to find, and then the upper angle, then the lower angle would be 90 minus 40.5. Okay? Yeah, that's fine. You can make whatever triangle you want. I made this one, so. Remember, cosine always is the side next to the angle. Sine is always the side across from the angle. So as long as you look in your triangle, that's why I don't like to say horizontal is always this, or vertical is always. Look at your triangle and decide on across from and next to. So, and then now I just need to do that calculation. You okay doing that calculation in there? Okay. What about, and then so, then for, to find the W, I'm going to use sine. Sine of theta is opposite over hypotenuse, which is where the so in SOHCAHTOA comes from. So sine of 40.5 degrees equals W over our 735 kilometers per hour. And then, again, I'm going to rearrange by multiplication. 735 kilometers per hour times sine of 40.5 degrees equals W. Yeah, good. And then we wanted to move on to the second part, part B, which says, okay, so you know how fast they're moving. How far do they move now? Yeah, but you're going to see what to do. So I know, I want to just find, I'm going to do the westerly, and if I do the westerly, you'll see the northerly. So I'm going to do my 735 sine of 40.5. So I get for my west here 477.344 kilometers per hour. And now I know that to the west it's moving at 477 meters per second. Let's say it's moving at 500 meters per second to the west. How far is it going to go after in 1 hour? It's moving at 500 meters per second to the west. How far west is it going to go in 1 hour? Sorry, I'm saying it wrong. If it's moving 500 kilometers per hour, how far is it going to move in 1 hour? 500 kilometers, right? Folks, is anyone engaging in this conversation and didn't understand that, or am I just? I know I'm putting it out in general, but why? Every hour, yeah. And then, so in 3 hours, I move 3 times this distance in the westerly direction. If you want to put an equation to it, that's a fine way to do it. If you want to put an equation to it, the equation you would put to it is d equals d naught plus v initial t plus 1/2 a t squared. It's not accelerating, so that part's gone. It starts at 0, and so you get d equals v times t. And so my d is, I don't know. In this case, I'm just going to do the westerly, so 477.344 kilometers per hour multiplied by 3 hours, and I get the correct answer. But I think it's better. It's also good to understand that every hour I move that far, so 3 hours, I move 3 times that. You got it, Isaac. All right, we're going to endeavor to get 6 done here. Number 6. Number 6. In number 6, we're given the path the truck follows, and then asked to find its displacement. Remember, displacement goes directly from where you start to where you stop. So I'm gonna block out my path here. Let's see, 23 blocks south, and so I'm gonna go 23-ish. That looks like 23 to me. 14 blocks east. So this is 23. This is 14, and then 21 blocks north. So just there. That's the path it tells me I follow, right? My displacement now is going to be from where I started to where I ended. So that's my displacement, that blue arrow. I'm going to draw the blue arrow a lot bigger, okay? I'm going to draw my blue arrow nice and big like that. Now here's the part about the direction that's probably causing misunderstanding, and this is the part that may be different on yours. Notice the direction they want counterclockwise from east is positive. So if I'm looking at my blue vector here, they want me to say, okay, east, which in my drawing is this way, they want the angle that goes from east counterclockwise all the way around to my blue line. Yeah? Now, let's say yours didn't point in my direction. Let's say it pointed this direction. Right? Did anyone's point down and to the right, down and to the left? Okay? If it's down and to the left, there's my east. They want this angle. Anyone's point down and to the right, like this. Oh, mine did. So we already did that one. What about up and to the right? Did anyone's point like this? Okay. Yours did? So up and to the right, they want this angle. What about up and to the left, like this? Did anyone's point in that direction? Yeah? They want this angle here. Each of these is handled slightly differently. All right? If you have this one, I would divide this. I know from here, right here, to right here is how many degrees? 180, and then I would find this inner angle and add it to 180. If you've got this, you got the easy case. You just find this inner angle and you've got your angle. This one, the bottom one here, straight up would be 90. So I would find this angle that I've just double arced and add 90 degrees to it. If you've got mine, we have two choices. We can either, well, with all these you have two. We can find this, an angle here, and then add it to 270. That's what we're going to do. Okay? So if I draw my components of my blue, I have down like this and across like that. That's at a right angle. Right? So, and I think about this blue part of this angle is 270 degrees, and then I have this little part that I haven't marked. Let's mark it in red. I have this little part, and that's going to be the angle that we'll call theta. So the red part here is theta. Because I know in a circle there are 360 degrees, and I'm 3/4 of the way around a circle, which is 270. Because a quarter of a circle is 90 degrees, a right angle. So 3 of those is 270. Yeah. So you formed your triangle like this. Okay? This angle here that I'm going to mark in green is the same as this angle in here because they're alternate interior angles. So if you find this angle in here, then you have that angle. All right. I know the length of my legs here. My horizontal one is 14 blocks. My vertical one here that's pointing downwards is 2 blocks. Right? From my diagram, because I only have 14 in the horizontal, but I have 23 and 21, so I end up with 2. I looked and I went 23 down and then 21 back up, which means I had a net movement of 2 down. So now that I have my triangle, and I have my legs, I can find my length. Let's call this length C. And so I can use Pythagoras to do a squared plus b squared equals c squared. 2 blocks squared plus 14 blocks squared equals c squared. Can't do that in my head. I get 14.14 blocks for my answer for the magnitude. Now, does yours look like mine? Okay, so watch how I do the direction now. I want to find theta. I know the opposite side and the adjacent side, so I'm going to use tangent, toe. So I know that tan of theta equals opposite over hypotenuse. Opposite over adjacent. Thank you. Wow, I've been doing too many sines and cosines. So tan of my unknown angle equals 14 over 2 for me. Right? Yes? Opposite over adjacent. Toe. Here's the tricky math part that you just kind of have to remember. To get the theta out of the tangent, I have to do inverse tan to both sides. So if I do inverse tan to this side, and I do it to this side, what that does is it crosses out them on this side, leaving me with theta. On this side, that function works on my 14 blocks over 2 blocks. And I come up with a number. In my case, and if you need to know how to put this in your calculator, you can see me and I'll up to that. I get theta equals, in my case, 81.87 degrees. Now, that's not my answer yet, because if I look back up here, I wanted this whole big angle. So in my case, it was 270 plus that. So my final answer is going to be 270 degrees plus 81.87 degrees, which is going to equal 352 degrees. If you have the one that you're talking about, then that's your answer because you didn't have to add anything to it. Let me just double check that I'm thinking correctly, because I need to send you away. And I did. Good. So remember, this one is going to vary on what you do in this final black step, depending upon which of these angle situations you have. Depending upon which angle you're going to find. If yours is like mine, I had to add 270. If you like this top one here, you have to add 180. If you're like this one here, you can just use the straight angle depending upon which one you found. Down here, the last choice here, you have to add 90 to it. So it depends upon how yours is arranged.